this computer. Awesome. So welcome to the sixth lecture on NLP with deep learning. And today it's not live here in the lecture room, but anyway, it should be interactive, as I said before. And what we're going to be talking today is we talked last week about narrow language models. So let me see if can see some people here. No. But anyway, I'm just assuming you're there. Last week we talked about standard language models and counting engrams and their limitations, and said like, well, basically, you can use them for generate language, for example, if you want. And today we're gonna extend this to, and also we talked about softmax, so very important thing. Today we're gonna talk about narrow language models, so extension of language models to use deep learning, and how to learn these so-called word embeddings and what these things are. So, well, a little bit of motivation here. So at the end of this lecture, um, or let me ask the other way. So if I give you a large corpus of plain data, so large corpus of the internet, we talk, what is it to get the internet? Can you build a model or system that will answer any of these word analogy tasks? So, for example, Germany to Berlin is like France to, what would be the answer? I guess Paris would be the capital, right? I mean, Germany to Berlin is like France to Paris, and man is to king like woman to, and the answer should be queen. So it seems like solving this task is kind of, it really needs some knowledge about relationship between words and things like this. So it's not that trivial. It looks much harder, maybe, than the standard, let's say, sentiment classification over movies, maybe. So can you solve this? Can you build a model for that? Anyone? If not yet, that's great, because after this lecture, we should be able to do so. So this is the motivation. But first, this is like really something very rudimentary. We need to talk about the dot product first. So what is the dot product? I mean, everybody knows that, I guess, from linear algebra and everywhere else. What is dot product? But I would like to build more intuition in the dot product and of its geometry, because it will be super helpful not only for this lecture, for others, but especially today for understanding some decisions in the models. So what is a dot product, by the way? So let's start with the dot product. It's let's say for two n-dimensional vectors u and v. So we have u and v here. How do we define the dot product? So I think you might remember it's we have, well, basically two definitions or two kind of notions of dot product. So one is the algebraic. We have two vectors and we basically multiply for both vectors. We go through dimensions and multiply values at their particle position and sum them up. So this is the algebraic thing, and yeah, okay, why not? It also has a geometric interpretation. If you look at this as 2D space with x1 and x2, and again these u and v vectors, then it also, and this is by the way the norm of a vector, so the length. The dot product is the product of the sizes of the lengths of the vector times cosinus of this theta angle. So this is the geometric thing, and also we can use some it has something to do with a scalar projection as well. So for example, if we project vector u on vector vector u down here on vector v, so we see some where we at vector v, and we can compute the length simply by trigonometry. So this is the formula. So this is two views on, well, one view on geometry of the dot product, and more onto what does it mean for unit vectors? So to build even more intuition on the dot product. So we have unit vectors. So what does it mean, unit vector? I mean, they have length one, right? I mean, u and v have length one because they're inscribed in this circle of radius one. Okay, so sounds good. So again, the definition for the dot product is two norms of the vector multiplied by cosinus of this theta angle. And since these are one, we get just, this is the dot product of unit vectors is the cosinus of the theta. Okay, cool. Sounds great. So what is the cosinus of the theta? I mean, everybody knows the cosinus function. So here the theta is something like, I don't know, 45 degrees. I guess this is exactly 45 degrees. And for 45 degrees, we are somewhere here, and the exact value is 0 0.7. Okay, well, this is interesting. So we know the maximum dot product or cosine similarity for unit vectors is 1, and the minimum would be -1. So for example, if we had U and V, U and W, excuse me, U and W are now orthogonal, so with 90 degrees to each other, there I have the zero dot product, and also if they're pointing to both completely different directions, their cosinus similarity is -1. So they're somehow least similar, so completely opposite. And this notion on similarity, like how vectors are similar and dot product, it might play a role later on. Okay, so far so good. I don't see any questions. I don't hear anyone, so I'm assuming like everybody's fine. Good, should be. Well, this shouldn't be surprising, but just well, now we see well that okay, dot product we never have normalized U and V. So what we're gonna do instead is to look into some relationships. So the dot product is actually unbounded in real numbers because if we have, I mean, these two U and V, these two they are larger than zero, right? I mean, this is looks like that. So there is some non-negative or non-90 degrees angle, and they pointing in similar direction. So this will be positive dot product, right? Well, if we make another vector W here, which is larger, so obviously the dot product of these two will be larger than the dot product of these two, and it will be positive. Okay, interesting. If we have, of course, U and Y here, these two vectors, these will be negative because these are opposing directions. So this will be on this side of the equation. And again, if we extend the Z to the left, making a larger vector, we still have a more negative cosine similarity. So the question you may be asking here, okay, yeah, I see the relations, makes sense. It's unbounded. Is it somehow related actually to distance of these vectors? Like if I'm making the cosinus similarity bigger and larger, am I moving the Euclidean distance somehow? Because I mean, we can think about similarity also like how close to each other these vectors live in the vector space, right? And the answer is, well, actually, yes, there is some pretty similarity in here. And so just for to recall, like what is Euclidean distance is the shortest distance between 2 points in the Euclidean space. So the Euclidean space is somewhere like the standard space, kind of. And this is how it's computed. So it's the Pythagorean theorem, but kind of generalization of the Pythagorean theorem. So it shouldn't be surprising, of course. And if we take the square of the Euclidean distance, so we take the Euclidean distance and make it squared, then we can do a little bit of algebra, which I'm going to skip for now. I mean, it's not important. You can just follow it. And after just a couple of multiplications and summations and reorganizations, we end up that the square of the Euclidean distance is, well, actually two dot products of, for itself, minus two dot products of these two vectors. And if these were unit vectors, so this and this were unit vector and the V were unit vectors, then we get this expression. So what does it say? Well, there is some relationship, and it says that, in other words, that if we want to minimize the square Euclidean distance, so minimizing this, making it smaller, means it's proportional to maximize cosine similarity, and it will be equivalent for unit vectors, but proportional in if these are not unit vectors, right? So if we're making this smaller, we're making this larger. Okay, cool. So actually, cosine similarity tells you like, oh yeah, the bigger the cosine similarity, the closer to each other these things are, and I can minimize one or the other. So if I want to move two vectors in a vector space closer to each other, which means I'm minimizing the square Euclidean distance or Euclidean distance squared, because minimizing squared something is sort of similar to minimizing the distance. Um, well, not really, just one part of it. If I'm minimizing that, I'm also can do it by maximizing the dot product, and this will be important later on. Okay, so this is why we're talking about the geometry of the dot product. It's kind of like a detour, but a kind of a interesting background that will be helpful. So, any questions so far, or any comments? Everybody's happy? Some people are coming, some people are leaving. This is great. Okay, so I don't see anything in the chat. So let's move on. And now let's come back to language models. So let's revisit language models again. So what was the task of language models again? I mean, if I were in the lecture hall, I would just ask you, but I'm not because it's kind of not really working now on Zoom. But let me just refresh it. So a language models as a conditional probability predictor. Well, yeah, this is language model predicts probability, right? Given a sequence of some keywords, give me a probability distribution of vocabulary for for the next possible word. So this is the language modeling thing, conditional language modeling. And in detail, it means like, okay, well, I have the sequence of 1 to k previous words, and I'm conditioning on these called sort of random variables. And I want to know what is k plus 1. What is the probability of k1 being particular word v? And I want to know this for all possible words v from our vocabulary v, like capital V. So this is again the language modeling task. And here's an example, just really refresher. So here's a sentence in English. So I'm just gonna read aloud, and you see you can fill the gap. So so I was at this party at Joe's place last night, but man, I was so tired. So like at about midnight, I said, Joe, I'm and blank, and this is the word you need to predict. And basically, you model this as give me probability for each word in the vocabulary given the previous, length. Excuse me, length. Sequence of length k. And of course, I mean, we might be guessing that the higher probability will have words like, well, I'm leaving, I'm out, I'm calling it a night, or I'm gonna head home and stuff like that. And other words like I'm hungry, maybe less likely. If you're tired, you might be hungry, of course, but you're leaving here in this example, and you're not gonna say I'm in love. Well, maybe I don't know. So fill the gap. I mean, we need to estimate these probabilities. So far so good. So this is language modeling again. And now let's think about this problem again. So I'm gonna come back to text classification and see like whether there is a parallel between text classification and language modeling. Like because these look like two different things. Like text classification is like classifying things into classes, positive, negative, I don't know, sentiment analysis, or movie or document genres like sports, politics, travel. And this is language modeling, like predict an expert. So why should we care? And here's the thing. So, and again, like I'm gonna write a text here for a text classification. So given a text, predict its label from a set of arbitrarily ordered items. So these are the classes such as sports, politics, travel. And we model a conditional probability for each label, a probability distribution over all the classes. So for example, if we want to classify this into sports, politics, and travel, we want to have a probability distribution of, what is a sports, politics, and travel as a sort of like a histogram. And this should sum up to 1 to have a proper probability distribution. And how are we going to do this? For example, if we build something we discussed last week, some multi-layer perceptron, back of words. I mean, we know how to turn text into a feature vector, right? We have, for example, back of words. And we put softmax on the last layer and we get a probability distribution. So this is a standard classification task. So why these things are highlighted here, you will see in a second, because now I'm gonna describe language model with the very same description sort of, but just changing these highlighted words. So language model, given a text, yeah, here I think I wrote like we already know how to turn text into a feature vector. So this is good. So for language models, given a text, predict the next word from a set of arbitrarily ordered items, which in this case is the vocabulary, like all the words. And we model conditional probability for each word, a probability distribution over the entire vocabulary, for example, by softmax. So you might see These two things are actually the same task. They just work on different, let's say, entities. And I believe this is something like, maybe it was clear from the very beginning for people working language modeling and text classification, maybe not. But it was really, at least to me, helpful like to understand, well, language modeling, of course, I mean, what's the next word? But we can model it as actually text classification. Can you classify an existing text uh, into set of words? And we can, well, this is not what we're doing, but we can model it as such. We can model it as such. We can model this conditional probability as classification task and run the same thing we know for text classification, right? So, and this is exactly what we're gonna do. Any questions so far or any comments? Well, not really. Okay, so I believe this is somehow something you should think about it for a while because then it will make sense like what a language modeling is all about and why it looks like classifiers all the way down because they are. We are basically classifying stuff or using supervised classifiers to do language modeling. Okay, so now we know something about language model and we know how can we build them. And we already know this from the last lecture. Like we can build classifiers for text classification, right? We did this for movie reviews, like multi-class classification for genres and stuff like that. So let's do language modeling with neural language models. Like let's build a neural network. So again, here's the description of the language model as sort of text classification again. And let's build a neural network to solve this task because why not? So what's going to be the input? I mean, the input is a k-gram of some words, 1 to k. And the output is the conditional probability distribution over the vocabulary V for the next word WK plus 1. So here's a quick question to you. If we're doing so just coming back here, if we're classifying into sport, politics, and travel, we have 3 classes. If we're classifying into the vocabulary, how many classes we have, roughly? Somebody in the chat or say loud. Okay. I see something 200,000. Yeah, yeah, that's a fair deal. Something like 200,000. So why not? If we have 200,000 vocabulary, we have 200K. Okay, it's well, oh, interesting. So this is really kind of hard classification task. So is it even possible? Yeah, so I mean, of course, I mean, you cannot really classify exactly because we will see later how we train these models, like the signal, what we are actually training on. But conceptually, this is the same thing, like multiple classes, just way too many. So thanks for the first inputs to the chat. You deserve something today. Okay, so we have this vocabulary V, and okay, so this is the input and output, and we're classifying into very large number of classes. Good. So one thing which will be important here is the so-called embedding layer. And maybe I could start with a picture. No, I'll start here. So, well, the inputs are words, and these are symbolic categorical features, right? So these are some like one hot encoding of words, for example. But we actually want to associate each possible feature value, so each word in the vocabulary with a d-dimensional vector for some d. So we want to do mapping from one hot of size of the vocabulary to something of some vectors of size d. Why are we going to do this? Well, there's multiple reasons. Well, let's take it now for granted we're gonna do this because it turned out like this mapping will be somehow very helpful and these embeddings will learn something very meaningful. But just for now, like pretend we want to get rid of these one hot vectors. And this is something also I guess we discussed last week in the learn representation. So we want to learn better representation of words. And how we do this is by mapping from one hot to some lower dimensions, for example. And of course, these vectors for words will be also parameters of the model, and we will train them with other parameters. So how exactly this embedding layer look in detail is Well, we have a matrix, so mapping from a symbolic feature such as word number 48 to this lower d-dimensional vector is performed by this embedding layer. It's sometimes called like a lookup layer. And well, the parameters in the embedding layer is a matrix E of this dimensionality. So let's say we have 200 words. So let's say this is the matrix E, and the dimensionality will be 200k because this is the size of the vocabulary. And this will be, I don't know, let's say 50. Why not? D is 50. And then for each word from the vocabulary, well, we just look it up. So if we have the 48th word from the vocabulary, we just go to position 48 here. And this will be the vector representation for word 48. Okay, so yeah, that's what's in here, well, these are parameters which we will train. So we'll get later to that, how to get there. But anyway, let's pretend we have this matrix. So we just look up each word and turn a index or one-hot encoding into a dense vector of size 50 from 200,000 to 50. Okay, interesting. And then if the symbolic feature is a one-hot vector x, so one-hot vector again, if we have x is one-hot vector um, of size, again, what is the size of one-hot vector? Well, the size of the vocabulary, right? So, which is 200k again. And it will be 0, 0, 0. Position 48 will be 1. And then all zeros. Well, then the lookup operation is actually just the multiplication x time e, right? So if you multiply x time e, so this is the matrix E, we are just laying this kind of like here for each of them, and you might see, given the 0 and 1, we basically effectively filtering out just one row here of this matrix. So, and as you might see, like multiplying vectors and matrices is something we want to do because it can be implemented fast, and we know how to do gradients over multiplication, and this is all nice and shiny. So this is the lookup operation, right? The idea again is we have a word of some very high dimensionality, and we want to turn it into some lower dimensionality. And we hope this lower dimensionality will be better representation of the word. Any questions? Sounds great. Okay, so let's move on. Okay, so what is the task again? We want to build a neural network. Okay, so we have the input is the words and the output is the words. So now the question is like, how do we model the context? We have k words. Let's build a network right away. So let's say we are taking k equals to 3, and the dimensionality of the word embeddings layer is 50. Okay, this is same what I had in the previous slide. So, okay, let's have a look. I mean, it looks kind of complicated, but okay. So let's start. Okay, I'm sorry. So we have the input words, the previous words, the black dog, and this is the context, and we have we want to predict the next word. So we want to predict what's the next word. Maybe I don't know. Well, distribution over the vocabulary. So this is the context. We take each context word and perform this lookup operation of this embeddings matrix. That's what we discussed in the previous slide. So each of those lookup operation will give us a vector of size, a single vector of size, what was that embedding? 50. Okay. So this is a size 50. Oops. Let me just make it much clearer. 50. So this will be size 50. Again, this is a size 50, and this is also size 50. We have these three vectors, and the easiest way to stack, well, not the easiest, one of the options to take three vectors together is just to concatenate, right? I mean, what is concatenation? So if you have one vector A and vector B, the concatenation of A and B is just you put them after each other. So it will be one large vector. C is concatenated, and it will be like 100 dimensionality. So we concatenate these vectors. And this will be our input X. So this is how we got from 3 words. So these were like backoff words or indices. We look them up, turn them into these so-called embeddings. For these embeddings, we are relying on this matrix E. So this is the embedding matrix. And so far, so good. So we have this input. And then the rest is something we saw before. I mean, this is the standard multilayer perceptron. So we have weights and biases, and there is one linear projection here, followed by some nonlinearity, could be ReLU, for example, why not? And then the next layer is simply a softmax layer where we, again, weights and biases. So first linear projection, then we put softmax on that, which gives us some probability distribution over the this is probability distribution over the entire vocabulary. And of course, the L is the loss here, and the Y will be the gold label. So this is the gold label. Well, in this case, the gold label is the next word, the next word. And again, how do we model an expert here? Well, this is a question. Well, the same way as we model the words at the input. So this will be one hot again. And you might see we have one hot here, we have a distribution here, and we want to make them as this loss could be some sort of like what is the loss? Categorical cross entropy loss would be the choice. And we want to make these two as close as possible. So this distribution should be as close to this one hot label. So basically, this word, which should be predicted, should be the most probable here, and the rest should be less probable in this distribution. Okay, so this is basically the network we are going to build. So very simple concatenation of 3 embeddings, and then multi-layer perceptron, just one layer, maybe hidden layer. We could do more, but it's just a simple one. And loss, and that's it. And the only trainable parameters are these weights and biases, and of course we're training the embedding matrix. Any questions? So it's not the case. Well, you might have. I mean, if you have question later, you can also like ask in our what we're using Discord or on YouTube as well. So that's fine. I'll be happy to address questions on YouTube as well. So this is very nested notation, so let's simplify a little bit. So we're gonna cram the lookup as simply the V node here, and the linear layer with parameters, I just turn it into one box like linear, and the W1 and B1 are the parameters. This is the nonlinearity and so on. So this is, again, the black dog, and here the gold label is barks, and here I'm saying explicitly. So all these words are one-hot encoding in the size of the vocabulary. And the loss, of course, I mean, if we're predicting the next word, we don't compute the loss. So from here, so this is for, let's say this is for inference, or if you want to generate from the model, and from the loss, this is interesting or important for training. And now talking about training. So we have the model, we know how to train a model. So just, quickly stepping back, like, well, we have a neural network. We can train it. We're going to train it as any other neural network. Stochastic gradient descent and backpropagation. So this is the computational graph. We know how to run efficient backpropagation. Excuse me. We know how to run efficient gradient computation on this computational graph. So we're gonna run backprop, and we're gonna do this iteratively over instances in training data and minimize the loss as long as we can, and it will learn the model. So we know how to do that. The question is like how to get the training examples for this. So how can we train such a language model? And this shouldn't be any surprise because this is similar as we discussed in the standard language models. So where to get training examples? Well, we take simply word k-grams from an unlabeled corpus. So we just take the internet, like the internet or some other textual corpus, text corpus. so-called, these are called corpora, corpus. And we take the first k minus one word, so the previous context as the input features, as the x. And the last word is used as the target label for the classification, xy. Done. I mean, the cross-entropy loss, of course. This would be like the choice of the loss. So this should be basically, I believe you should be now in a position to build this. Maybe like excuse me, the embedding layer shouldn't be actually tricky because the lookup operation is also a node. I mean, we didn't implement it in our tiny little network framework. We didn't implement this. We neither implement the concatenation, but it shouldn't be super hard to do this. And the rest, I mean, we can implement softmax, loss, and stuff like that. So we should be able to build basically this whole thing, the neural language model from scratch in our tiny little net framework. And that could work. I mean, of course, it will be super inefficient, and I don't know if it actually will train something meaningful, but basically there's no magic behind. Okay, so we have training of neural networks. What are the advantages of these neural language models? What are the advantages of these neural language models? So if you remember the standard language models, like they suffered, so the Ngram language model, right? They suffered from the explosion of parameters, because if you have like trigram model or four-gram model, so you have four consecutive tokens after each other. And if you want to build 5-gram language model, your number of parameters will be multiplied by the size of the vocabulary. So if you have 200,000 vocabulary model, then unigram model is 200,000 parameters. Bigram model is 200,000 parameters squared. Cube with 4 to the power of 4, with 5 to the power of 5. So many parameters you need. And then you will have actually a hard time to find, all these 5-grams and stuff like that. So standard language models, like Ngram language models, their parameters for the better context scale exponentially. Here, the neural language model, there is just a sort of like approximately linear increase in parameters if we add more context here. So it's really better than classical language models. So which means we have less parameters for larger context, and the chances are it will learn better. And that's actually true. So I mean, these are somehow this all neural language models are based on papers from, if I'm not mistaken, from Yoshua Bengio and his team from 2003 or 4, I guess Norris papers or GMLR papers. And they showed like these neural language models are actually, they have better perplexities than the standard models, and they showed a couple of tricks. So it's not at all, I mean, it's, Ngram language models have been here for decades, neural language models, early 2000 maybe. Okay, so what is important here also, that by learning these, it turned out that by learning these language models, not only we can predict the next word or make, probability predictions about the possible next words, but also this E learns something important or interesting. So each row in this embedding matrix learns some sort of word representation, right? Remember, we are talking a couple of slides back about projecting one hot word into some low dimensionality, like 50. So this would be of dimension v times 50. So now we can express each word as some sort of real numbers, so dense representation of size 50. And these representations have some nice cool properties which we can utilize and exploit further. So these are called word embeddings, and we should spend some time on them because this is like very, very crucial concept in well, embeddings are actually the crucial concept in deep learning for NLP, and word embeddings is like a cornerstone of that. So what are word embeddings and how to learn them? Any questions so far? Comments? We're good. I think we're a little bit fast. Well, it's good. I mean, it's a different setup, so it's less interactive, but let's get it across. So let's start with learning word embeddings and the so-called distributional hypothesis. So what does it mean? So what are the, okay, one-hot encoding of words? What is it again? So we have vocabulary. So let's say this vocabulary have only 3,000 words, just very simple. And each of word like nice, pleasant, and horrible are represented as just one and zeros everywhere else. So one at position something, something, something here, something here, something here. And everywhere else there are zeros. The thing is, the major drawback is that there's no semantic similarity of words which are actually similar. You know, that's the point. Like, for example, nice and pleasant and horrible, they are very distinct categories and distinct kind of positions in this space. And there's no notion of like, well, these vectors should be more similar, all of them somehow together, than, bad and ugly and all these vectors. No. Have you heard about the word Hamming distance? Anybody here in the audience? Hamming distance.
Yes, but I don't remember.
That's okay. If yes, and you don't remember, well, I'm just gonna tell you like all these two vectors have Hamming distance too. Well, this is basically the number of different elements in the vector. So each of those differ in exactly two positions. So all of them have the same distance from each other. Hamming distance is two. So there is no ordering. You cannot do anything about it. Like they're just, so far apart, like everything is treated equally. No notion of similarity. So yeah, that's bad. Because I mean we should know somehow, like if we have vector for words, these should be somehow closed in the space of the vector space. Maybe, because it could be helpful for generalization, of course. So here's the distributional hypothesis, which dates back to maybe like 1950, well, absolutely 1950s, but maybe even like 1930s, some works in linguistics. And it says that, nothing surprising, words that are similar if they appear in similar contexts. Yeah, of course. This is maybe how we learn. I don't know how we learn language, but we are utilizing this. Like if we don't understand a thing, we can kind of infer what is it. So intuitively, when we encounter a sentence with an unknown word, such as the word Wampinuk. Okay, so this is cool. Anybody knows what a Wampinuk is? Any guess? What could Wampinuk be? Well, I have no idea here. Maybe the word doesn't exist. So now if I show you this sentence, Marcos saw a hairy little Wampinuk crouching behind a tree. Now you know what Wampinuk is. Well, you don't know what it is, but you can infer it's something like tiny little creature, maybe hairy, crouching behind a tree. So I don't know. I mean, if you need to draw a Wampinuk, it would be something like there's a tree and there is a tiny little Wampinuk. And now it's not a unknown. Well, sorry for this. Uh, Now there is no, you don't know what Wampanyuk exactly is, but you can kind of infer it from the context. So we infer the meaning of the word based on the context in which it occurs. Okay, so this is the basically of distributional hypothesis. So we use the context to understand the meaning of the word. This is this is a deep thought, but it makes a lot of sense also, like common sense. So, and we're gonna use this notion for learning or understanding, word semantics or meaning of words. So by the way, I mean, I asked people to draw one pinuk on the last exam, and it was really fun. Maybe we're not gonna do this year because first I'm telling you so, and second we're gonna do it electronically. But it was quite fun. Okay, and also show like who paid attention in lectures or not, because then you saw like, well, who didn't see the lectures, no one pinuk in the exam. Anyway, so here's the, let's move from narrow language models to training word embedding. So we have the narrow language models, of course, they can predict the next word. And we want to learn these word embeddings, so like dense representation of words. So narrow language model's goal is to predict probability distribution over vocabulary for the next word. Okay, so we know this. And the side product is that it can learn some useful word embeddings, of course, yes. Um, Yeah, but do we really, I mean, if we want to just, I mean, this is a side product, so it learns some useful things. But what we make this as a target? Like, what if we don't need a probability distribution, but just want these learned word embeddings? What if we just don't care about the probabilities and stuff like that? So there's two tricks we can use to make it work better for the word embeddings and actually faster and learn something very helpful. So remember we have this, what was the Markov assumption? Did we talk about this? Like looking only in the, k previous words in the language models, not the whole history. So, but previous words, right? We are just looking always in the past, never into the future. Maybe we can just get rid of this and look into the future. Why not? Because we're not now predicting the next word. We will just learn word embeddings. And yeah, and there is in the softmax, we can get rid of the costly normalization. Okay, so there's some tiny little technical details which make it faster. But let's start with the first one. Simplification number one, ditch the Markov property and look into the future. Oh, wow, wow, wow. Okay, looks like cheating, but no, I mean, we don't care about predicting the next word. We are interested in learning best embeddings here. So what we're gonna do is instead of predicting the black dog barked, we just take the middle word here, the black. This will be our gold label. And we want to predict the missing word, like in the middle, right? I mean, the rest of the architecture is the same as we had before. Like we have this lookup table, we concatenate these two vectors, the context, we have hidden layer, nonlinearity, hidden layer, softmax, and so everything stays the same, but we just ditch the Markov property and not predicting the next word, but the word in the middle. Why is this so? I mean, of course, in the Wampinu case, is we just come back as a Marcus saw a hairy little Wampinu crouching behind a tree. So, I mean, the context on the left and right are important for the remember knowing the word Wampinu, not just on the left. So we need both to better understand. I mean, we utilize both to better understand the word. Maybe left would be okay, but the more, the better. And since we are not predicting the next word, yeah, why not? We're just predicting the missing word. So this is one simplification. Any questions? Does it make sense? Are we cheating? Not. We're not cheating. We don't care about predicting the next word. This is not language modeling now. This is how to learn better representation. So we kind of, changing the task a little bit. So instead of modeling, the next word, we just model the missing word here exactly. So this is the first simplification. And the second one is that, well, okay, we still have this softmax here, and it's gonna be the softmax is actually quite costly because why? If we have the V size is 200K, and if you remember it's a softmax, you need to do the exponentiations of 200,000 items, do the sum, normalizing. So it's kind of like costly operation. So it's really prohibitive if you do it over large vocabularies. It's been shown like, yeah, this really takes time. But wait a second, I mean, we don't need a probability. Like just give it up. Just do something else. So we just give up this costly probability distribution. We just don't care. And instead of predicting the probability distribution over the entire vocabulary, we just want to predict some score of context and target word. Okay, so context here, this is, oops, excuse me. This is the context, left and right, and this is the target word. And we want to somehow predict the target word given the context. Okay. And give it some score. So what the score should be. So we should prefer words if the target words, if they are in their true context, so the right context. And we should penalize words that are in some untrue context. Looks somehow weird, like what is a true context and what is untrue context. But how we're gonna deal with this will be very clear right now. So now we turn our task, we make a little trick. It's called negative sampling. So instead of predicting the probability distribution for the target, we create an artificial binary task. So we're just creating a new task by choosing either the correct or a random incorrect target word. So what does it mean exactly? So binary task means like 0 or 1. So 0 or 1. So it will be 1 if the word is a positive example from the corpus. So for example, uh, the the black dog, dog, and this will be the target. So this will be a positive example. And it will be negative, excuse me, it will be 0 like a negative label, so 0 label, if the word is some random incorrect target word. So for example, we keep the context D and dog, and now choose some random word from vocabulary. I mean, what could be? Um, something very bad. The man. Well, it's not even something even worse. Uh, well, I have no idea now. What could it be? Some word that doesn't make any sense. The A dog, like A, like let's sample A. This would be a negative example. The A dog doesn't make much sense here. It's even like grammatically incorrect. And A shouldn't happen after D. So, well, there's something wrong. Okay, so I mean, we are just lucky of sampling something. Nonsense could be some other word like the cat, the flying dog. Yeah, that's a better example. So if we sample negatively random word, random incorrect target word, we have a flying dog, and it's it makes no sense here. So this will be penalized. Okay, how do we sample these words from the vocabulary? There's we can just use corpus-based frequency or something else. This is not really important, but there's some techniques used for actually sampling the negative examples. Okay, so these are, I mean, we're just turning this into simple task. Given a context and a, a target word, tell me if it's true or false. By doing this, we're simplifying many things. So let's look at the architecture now. Okay, so we turn the problem into binary classification, and here's a positive example. So we have again the black dog. So this is the context. We have this lookup table again. So the embeddings. We model the context somehow. We don't care yet how. We have the target word, also using through embeddings, and we combine it somehow. We combine the context and the target word somehow. We need to combine somehow. And then there is some hidden layers. So yeah. And now we're turning the softmax into, well, we have just binary classification. So this is a sigmoid. So now we have sigmoid, 1 or 0. So probability distribution between 0 and 1. And the loss will be binary cross entropy. And here, of course, this is a positive example, which means the gold label is 1 because we have the true word here. So this is the positive example and how the network could look like. I mean, there are some still open questions which we'll just solve, soon. But how the negative example would look like is this. So this is a negative example. And of course, we have some other word here, with. Okay, so it really makes no sense here. The with doc. And the negative means the label is 0 and the architecture is the same. And of course, I mean, we have now, again, how do we do the training data? I mean, we do the negative sampling. So we take a corpus, take the internet, and just take k word contexts or k grams, and take the target word and either keep it or replace it somehow. And this is artificial binary task. We created this data artificially, and we'll train this model. And by doing so, it should learn some good representation of words. So how exactly this will be? No, not how exactly. We know how exactly, but there are some still kind of open questions here, and we will tackle this in the next part. Any questions so far? Negative sampling? Okay, good. So we're leaving language models. We're not predicting the expert. We're just trying to make a nice objective to learn better word embeddings. That's the goal. And one of these examples was the word2vec, which used to be, well, maybe still is in some contexts, a very popular implementation of learning word embeddings, and really was part of the boom of deep learning in natural language processing in like 10 years back, 12 years back. It really showed like the power of deep learning and NLP. So word2vec, it even simplifies the narrow language model by removing the hidden layer. So we don't have any hidden layers anymore. And it just basically turns into log linear model. I mean, we have somehow combined these things, and this should be just a real number. So this should be some real number which we run through sigmoid and get a prediction. So we just get rid of the complexity. Log linear model. So this should be somehow combining everything into a number and show the strength of association. Okay, so this is really easy because the less layers you have, the faster you can train. Now the question remains like how to model the context and how somehow combine these two things. So how do we model the context, like the previous and the next word? We have the lookup. Okay, so these are vectors in our embeddings. So these are of dimensionality, let's say, I don't know, 50. And this is again D50. And this is again 50. So what is the easiest or one of the most simple solution of combining two vectors together of the same dimensionality? If you give it 5 seconds thought, you come with at least two solutions. So sum them up, take an average. The easiest one is sum them up. This is exactly what they did. So we just sum them up. Just take these vectors and just add them together. Works. Why exactly? Why is it not better than the average? Well, I don't know. I mean, there's some reasons behind that, some theory, but it was, I believe, a lot of experimental work as well. Like, just train it and see how it works empirically. So we sum up these two vectors together, and then yeah, okay. So we have a vector of dimensionality, let's say 50, and this is also dimensionality of the 50. So the target word is 50-50. Now the idea is how do we combine these together? So what are we gonna do? And now we're coming back to why we're talking about in the first part. So what we wanna do is if the correct word and its embeddings is in it's represented correctly by its context. So the context, if it's representing the word well, it should have some high score because we want to have this to be 1. So if this is somehow similar to this word, they should have high score. If this vector is not similar to this one, so the context does not really represent the word itself, they should have some small scores. And of course here, since here comes the real numbers, so we want to we have the full uh, real line. Oh, this is the wrong real line. I mean, no, real line like that. This is the real line. There's 0. So again, if we have contexts that are similar, so the sum of the context represents the word well, so they are similar to this word, it should be somehow positive, because when there's a positive value after sigmoid, it will be turned to 1. That's the sigmoid doing. If the context summed doesn't represent, so the representation of the context doesn't look similar to the target word, so this would be like negative target word, it should be repelled. It should be moved somewhere on the other side, very negative, because then we will get 0 here. And now, I mean, okay, how do you make this similar and not similar? This is why you're talking about the dot product. Remember, if two vectors point to the same direction, they look similar in the vector space, and they have a large cosine similarity. If they look to the opposite direction, so they are dissimilar, they have negative cosine similarity, unbounded. And this is exactly what we need here. So somehow combined, turn out this will be just the dot product. And the geometrical intuition behind should be now a little bit clear. Why is this so? Okay, this is it. And why is dot product good? Well, it's fast to implement. It's just a it's just a product of two vectors. Okay, so now again, we have here, I just reorganized a little bit of context here. So we have context of previous word and the next word, uh, turn into embeddings and sum them up. Now we have the target word, and this is again a vector, and here's the dot product. And if the dot product is large, this will be after sigmoid will be likely to be 1. And we want this to be classified as a positive one. If the similarity will be very low, so the word is not really modeled by its context words, then the similarity, then the similarity will be negative, which will the sigmoid will turn into close to 0. And this is what we want. Okay, so this answers the question, what is the sigmoid doing? So it's turning the cosine similarities into probability distribution. And what else is here? So the WI is the target word. This is the context, of course. And again, this is negative sampling. So Y equals 1 is for correct word context pairs, and 0 is for the random word. And the only learnable, now we just remember, the only learnable parameter here is the embedding matrix E. So this is the only parameters we're training. There's nothing else. There's no, I mean, just look here what we started with. We started with something like, yeah, we would have here the embeddings, and then this should be learnable, and this should be learnable. We don't need any of those. We don't need to learn anything except of the embeddings itself. And this is what we're doing. Everything here is just functions, and these are actually super fast. So sigmoid, easy. Dot product, wow, super fast. Summing two vectors, this is super fast. So you can really iterate over large quantities of input data. And the more you train, the better embeddings you learn. So this is really the deal breaker. So this concept is called also continuous back of words. Continuous back of words. There's another called skipgram as well, which is even more simplification. I'm not going to talk about this right now, but if you go down into the, not to the comments, go down to the appendix of the slides, there is more information about the skipgram. And there's another newer embeddings like fast text, but these are not super important. But just to thinking about embeddings and how to learn them, and to create the task for negative sampling is a cool thing. Any questions? Okay, it's not a case. So let's move to word2vec again. So summary of word2vec. It's learning useful word embedding. So we train the network to distinguish good word context pairs from the bad ones. Okay, good. We create a set D of correct word pairs and set D dash of incorrect word context pairs. And the goal of the algorithm is to estimate. I mean, we basically talk about this already. It should be high for pairs from D and low for pairs from the negative things. Yeah, of course. So we're basically learning, we initialize the embeddings randomly. And then by learning, we learn the vector space. We learn where the words should be in this space. So we're repelling words from wrong contexts and putting things together from similar contexts. And this is just doing by training the model to distinguish, yeah, this is true context, this is false context. So it's actually pretty cool that it works. So what are the advantages and limitations of word embeddings? Okay, so this is something to keep in mind. If you use it, maybe you're not use it anymore. Maybe you do in some context. I'll see one example where these could still be used. And what's the trick of using them? So, but how do we use word embeddings? So if we just pre-train word embeddings, which means, yeah, we run this word2vec or some other algorithm on the internal data, we end up with matrix E, the embeddings. And this then for each word, instead of having one hot vector, we have already a semantic meaning for the word. And we can use it for any neural network instead of one hot word encoding. So we have some better representation of word. And actually, this was really like why word embeddings really hit, or deep learning actually hit the revolution in NLP in 2015, 2014, even like 2013 maybe. Everybody just started using word embeddings and all the tasks were like, wow, way better, way better. Why? I mean, because now the embeddings have the ability of similar words have similar embeddings because they have appear in similar contexts. And now we have a meaning of these embeddings. Like, not, so excuse me, we cover the semantic meaning or some other meaning just better than one hot. One hot doesn't cover any similarities. In embeddings, they do. So that's why you can generalize from unseen words to and you know having if you have synonyms, for example, in many tasks, way better. So it's an instance of so-called transfer learning. So we pre-trained or self-trained also on some auxiliary task and plug it into a more complex model as pre-trained weights. Yeah, this is how it works. So for example, we can represent, instead of representing document as a back of words, we can represent it as the average back of embeddings. So back of words through embeddings for text classification. And voila, it really works. It's a really cool baseline. One-hot encoding is cool. Back of embeddings is even better. Sometimes it depends on the task, but in general, it's worth a shot. Like just take the embeddings and make it together, make the average. Okay. Now, of course, you can use this for some sort of semantic similarity or short document similarity or query expansion. So query expansion is interesting. If you search for something and you want to search for synonyms, you just use the word embeddings of the word and look for the closest kind of uh, neighbors. So we select terms that are semantically related to the query. So if you type something in the query search, like a word, and it will look up the word embeddings that are closest to each, in the embedding space and just, expand the query and look for the same words as well. So what can go possible, what can go wrong? Like why this could fail? Well, I give you one example, and this is not really old enough. Sorry, not old, not that old. So, everybody remembers the pandemic, unfortunately. So I think it's like 2 years back, actually. No, even like maybe might have been even last year. I don't remember, like 2 years back. So I was searching in, Reve for COVID test. And of course, I'm pretty sure they used some word embeddings because I typed in COVID in the shop, and what it gave me, is basically Corona beer. Yeah, I didn't ask for beer or anything like that. I just wanted COVID tests. And you might be, oh, okay, they're using word embeddings because if you train word embeddings on web data, COVID and Corona is basically will be very close to each other in the word embedding. Why? They appear this is the same meaning, but it cannot disambiguate here. It cannot tell like what I'm looking for. So it's bad. It's like a bad example, like why it fails. So query expansion with word embeddings might be tricky. And, well, yeah, of course, disambiguation. So when we want to, the question I asked, at the beginning of this lecture was, can we solve this task of Germany to Berlin is friends to Paris? We can actually use word2vec and the pre-trained embeddings to mine these word analogies. So for example, we can solve this by taking the embeddings of Berlin and subtract embedding of Germany and add the embedding of France, and it will give us a vector, right? I mean, these are all vectors. This is a vector, this is a vector, and this is a vector in the same space, and it will output a vector. And the vector is closest to Paris in the embedding space. And this is actually pretty cool. Like when people saw it for the first time, I was like, really? You can really do Now you can do mathematical operations on vectors, on words, and if you do subtractions and additions, you get some meaning. So in this space, the positions of these words to each other carry out some analogies, like or generalizations, like state and capital. And this is pretty interesting. This is just learned from data. I mean, nobody told it like, oh, by the way, here's the capital and here's the state and stuff like that. No, it just learned from context in the training data. And here's another one, like find the queen. So the king to the man is like woman to what? Yeah, to the queen. The same kind of analogy. So it's learning also some occupational positions. So there's a lot of in word to in word to vec embeddings and other embeddings if you train them. There's a lot of them, and the question is like, do we understand them well, and do they have any limitations? So this everything looks shiny and cool. There's been tons of papers showing, well, actually, this is not learning the actual analogies. It's learning more super, hierarchies like subordinate items and stuff like that. But anyway, it's still way, 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 way better representation than just one hot encoding. So what are your limitations here? And then we'll wrap up. So we started with definition of similarity, and this is like completely operational. So we just said like, yeah, you know what, words are similar if used in similar contexts. We never said like what similarity means. And the thing is like some things like antonyms, so words opposite to each other, like buy and sell, hot and cold, they tend to be in similar contexts because things that can be hot can also be cold, and things that are bought are often sold. So antonyms will suffer from word embeddings as we just did because they will be just judged, the models might judge antonyms as very similar, but they are not, of course. You want to have difference between buy and sell. Yeah, so this is one disadvantage, antonyms. Of course, we had ton of biases in the train data. If you train on anything on the internet, the distribution methods reflect the usage patterns in corpora on which they are tested. So I'm quoting from this science paper. Word embeddings encode not only stereotypical biases, but also other knowledge. And they are problematic as towards race, gender, or simply vertical, reflecting the status quo distribution of gender with respect to careers or first names. Yeah, so that's the biases are encoded in the embeddings. So, be wise if you use embeddings in anything downstream that you are aware of that, and maybe there's ways to counterfeit the biases in the data somehow. I mean, there's research on that. So this is one negative part of that. And also like more linguistic one, I mean, this is maybe the most important thing about word embeddings. These are context independent representation of a word. So, but some words have obvious multiple senses, so-called senses, like meanings. So for example, a bank may refer to these, to the financial institutions, Commerzbank, or to the side of a river, so riverbank, or what else? A bank you're sitting on in a park. A star maybe in a just an abstract shape. A star could be a celebrity. A star could be just stars on the sky. And in these word embeddings, as we talk about, they use a single vector for all these forms, right? You cannot disambiguate. So polysemy meaning multiple meanings of the word, but bank will always have the same vector, regardless of the context. The context won't matter because you just take one word, look up the embedding matrix, and get one vector all the same time. So this is one of the biggest limitations for word level word embeddings, and that's why after some period of kind of exploring word embeddings, researchers started to looking into, well, can I actually learn context, embeddings based on context? Can I learn the embedding of a word in a context? And I guess this is a story for next time. This is how basically all the transformer models start looking into. That's what transformers are doing. They're looking into embeddings in a context because This is the key disadvantage of just single word embeddings, is the contextual independency. So let me just recap here for today. Um, so we talk about neural language models and how they are better than standard language models. And then we say like, well, actually neural language models are good to not only to predict the next word, but they actually learn through doing this, they're learning interesting word representations in the embedding matrix, which might have motivated. I don't know how people came up to ideas, but I guess it kind of motivated people to explore these embeddings learning more and start into looking how to train only for these word embeddings and maybe like just completely get rid of all these limitations of neural language models and the softmax and things like that and just simplify and negative sampling. And for example, word2vec is really like one of the groundbreaking algorithms or set of, it's not an algorithm, it's a set of architectures and the choice of modeling context and the choice of creating the negative samples. And we talk about a continuous back of words for context modeling and talk about how these are used. Having said that, I think I'm through the lecture for today. So if you don't have any questions, or if you have any questions, I mean, I might stop recording right now and we can talk questions afterwards. So let me just stop recording.